Going through the examples from class, let's start with having a radical or a square root that does not have a perfect square. So our first example is square root of 48. So we're going to ask ourselves, what is the largest square root that goes into 48? That's a factor of 48. And our answer is 16. So 16 times 3 equals 48. So we're going to rewrite it as square root of 16 times 3. Square root of 16 is 4. So we can rewrite this as square root of 4 squared times 3. And now we can pull out that square, that perfect square. And so we can write this in its simplified version as 4 times the square root of 3. That's our final answer. Moving on to square root of 63. The largest perfect square, that's a factor of 63, is 9. So we're going to rewrite this as square root of 9 times 7. Let's rewrite 9 as 3 squared. So now we have square root of 3 squared times 7. And now we can pull out that perfect square to get 3 times the square root of 7. And that's the simplified version of square root of 63. So now let's try some that have variables. So we have square root of x squared. Let's go ahead and rewrite that as square root of x times x. Group up our pairs. So we have one pair, so we're going to pull out 1x. Square root of y to the 6th. Let's rewrite that. Square root of y times y times y times y times y times y. Group up our pairs. We have 3 pairs, so we're going to pull out 3 y's. So we get y to the 3rd. Looking at our variables in the square root and the variables in the simplified version, you can take the variable in the square root divided by 2 to get the variable in the simplified version. So on C, if you take 2 divided by 2, you get 1. On D, if you take 6 divided by 2, you get 3. So let's try this again. We have the square root of a to the 4th times b to the 22nd. So let's first look at a. Its exponent is 4. So we're going to take 4 divided by 2, which is 2. So we have a squared. Now let's look at b. We have b to the 22nd. 22 divided by 2 is 11. So our answer is a squared times b to the 11th. So now let's look at odd exponents, because that trick works for even exponents but not odd. So if we have square root of x to the 3rd, let's go ahead and rewrite that as square root of x times x times x. We can group up our pairs, and we have 1x left over. Pull out that single x, and we still have square root of x left over, and we cannot simplify that any further. Our shortcut is that the largest perfect square of an odd exponent will always be that odd exponent minus 1. And then we can use that trick with the even exponents. So if we have the square root of y to the 7th, we can rewrite that as square root of y to the 6th times y, because the largest perfect square that goes into y to the 7th is going to be 7 minus 1, which is 6. And we have one more y left over. Now we know that we can take 6 divided by 2 and get y to the 3rd. And then we have a y left over under that square root sign still. Let's do another one. This time we have a negative exponent. So we need to write the inverse of that. So we need to write it as a fraction. So we have 1 divided by the square root of w to the 5th. So remember that if you have a negative exponent, you're going to write the inverse. You're going to write it as a fraction and make that exponent positive. And now we can finish this one similar to the last example we just did. The largest perfect square, that's a factor of w to the fifth, would be w to the fourth, because 4 is 1 less than 5. And then we still have that w left over that's inside that square root. The square root of w to the fourth is w squared, and we have that extra w under that square root. Remember that that's all happening in the denominator, so that needs to stay in the denominator. Your answer needs to be the fraction. So now let's put this all together and practice a couple more. So we have square root of 8 times x to the third, y to the eighth. So looking at the 8, you can rewrite that as 4 times 2, and 4 is a perfect square. Looking at x to the third, you can rewrite that as x squared times x. And then y to the eighth is a perfect square, so we're just going to leave it as y to the eighth. Now let's go ahead and take out our perfect squares. So the square root of 4 is 2. The square root of x squared is x. And the square root of y to the eighth is y to the fourth. And then we have the 2x left over inside that square root sign still. This answer is as simplified as this problem will get, so we are done. And we can move on to the next example, which is 4j times the square root of 12 times j to the fifth, k squared times l to the sixth. Right now we're worried about what's inside that square root sign. So when we go through this, we're just going to rewrite 4j on the outside, and then we'll deal with that later. So let's first look at the 12. The largest perfect square that is a factor of 12 is 4. So we can rewrite the 12 as 4 times 3. The largest perfect square that's a factor of j to the fifth is j to the fourth. And so we'll rewrite that as j to the fourth times j. And then k squared and l to the sixth both have even exponents, so we can just rewrite those because they are perfect squares. So now we can go ahead and take out the perfect squares that are inside that square root. So that would be 4, j to the fourth, k squared, and l to the sixth. So I have my 4 and my j still outside of that square root. And then when I take out the 4, I'm going to multiply by 2. When I take out j to the fourth, I'll multiply by j squared. When I take out k squared, I'll multiply by k. And when I take out l to the sixth, I'm going to multiply by l to the third. And then I have 3j left over inside that square root. So one more step, I need to simplify outside of the square root this time. So I'm going to have 4 times 2, which is 8. J squared times j, which remember when you're multiplying variables, you're going to add the exponents. So 2 plus 1 is 3, so j squared times j is j to the third, and then you also have the k times l to the third. And bring on down that square root of 3j. All right, just a couple more. Now we have square root of 12 g to the negative 3, h to the fourth, I to the seventh, times the square root of 4g to the fifth, h I to the sixth. So before we do any simplification, let's go ahead and multiply those square roots together. So we're going to multiply all the coefficients and variables and put it all under one square root. So I have 12 times 4, which is 48. G to the negative third times g to the fifth. Remember, we're adding the exponents, so I get g squared. H to the fourth times h, so I get h to the fifth. And then I to the seventh times I to the sixth, so I get I to the 13th. Now we can simplify this. The largest perfect square that goes into 48 is 16. So I get 16 times 3 times g squared. H to the 5th is going to break down into h to the 4th times h, and I to the 13th is going to break down into I to the 12th times I. Now let's pull out those perfect squares. So I get 4gh squared times I to the 6th outside of the square root, and then inside the square root, I'm left with 3hi. Last one, this time we're dividing, so let's divide everything and put it under one square root and then simplify. So let's look at the coefficients first. 72 divided by 4 is 18. This time when we divide variables, we're going to subtract the exponents. So a squared divided by a to the negative 6, you're going to take 2 minus negative 6. So that would be 2 plus 6, which is 8. B divided by b, you would have 1 minus 1, which cancels out. And so the b's go away. And then c to the negative 1 divided by c to the negative 11th, you take negative 1 minus negative 11. So negative 1 plus 11, which is 10. So right now we have square root of 18 times a to the 8th, c to the 10th, and now we can simplify this. The largest perfect square that goes into 18 is 9. So we have 9 times 2. And then a and c both have even exponents, so we're just going to bring them on down. And now we can rewrite this. Square root of 9 is 3. Square root of a to the 8th is a to the 4th. And square root of c to the 10th is c to the 5th. And I have a square root of 2 left over.